Hello, welcome to today's physics lesson. Today we're going to learn about the rope swing problem. So at the beginning we watched the info video. They tell us that the length of the rope is 130 feet, which is 39.624 meters. The height of the cliff is 150 feet, which is 45.72 meters. And they tell us that at the bottom of the swing they are 10 feet off the ground, so we'll use that later. We took the average person's weight to be about 70 kilograms. And we're going to neglect air resistance in this problem and take our system to be the person, the rope, and the earth. So for the first problem, we're trying to find the velocity at the bottom of the swing. We're going to use the energy principle here and say that potential energy initial plus kinetic energy initial is going to equal the final potential energy plus the final kinetic energy, because the change in energy is going to be zero because the system includes everything that we're looking at. And we can set Ki to 0 because you're not moving at the very top of the swing. So here we have initial potential energy, mgh plus 0 kinetic energy equals mgh final plus Ki, or K final. And we solve that for V, and we get 27.87 meters per second. In this problem, we're treating the rope as an ideal rope where there's no stretch. So for this height, we just took the length of, or the height from the rock minus the length of the rope. Okay, so for the next problem, we're trying to find the tension now. So we're using this equation here, T minus mg equals F perpendicular, or mv squared over r. So we're taking the V that we just found of 27.87 meters per second, multiply that by our 70 kilograms, and divide by the length of the rope, and we have 1372.19 newtons. And then, so T is going to equal F perpendicular plus mg, so we add 70 times 9.8 plus 1372.19, and we come up with 2058.19 newtons. For the next problem, we're looking at when you are 30 degrees from the bottom of the trajectory. So this is going to be, you're going to be a different height off the ground because you're not at the very bottom. So that's what we're going to solve for first. So this L right here is going to be cosine 30 times the length of the rope, which is 39.624 meters, and that's going to give us 34.3159 meters. So to find this distance off the ground, we're going to subtract that from the total height from the rock, and that's going to give us 11.4046 meters off the ground. In this problem, it's the same as the one earlier, so delta E is going to be 0, so we can use the same energy principle where the initial potential energy plus the initial kinetic energy is going to equal the final potential energy plus the final kinetic energy. And once again, we're going to set Ki to 0 because he's still not moving at the top. So here we go again. We have mgh final, or initial, plus your kinetic energy initial, and we're going to set that equal to your final potential energy with the height that we just found plus your final kinetic energy. We're going to solve for V again and come up with 25.93 meters per second. So then, in this case, we have tension equals F perpendicular minus mg sine 30. We got that from the tension force is going to be F perpendicular plus F parallel. So this is F parallel. And so we're going to come up with mv squared over r with that same V that we just found, minus 70 times 9.8 times sine 30. And that's going to give us 845.079 newtons. So down here to number 4, they told us in the video that the height off the ground at the bottom of the trajectory is 10 feet, and since the length of the rope is 130 feet and you're starting 150 feet off the ground, we can assume that there's a 10-foot stretch in the rope, which is going to be 3.048 meters. And since we know our tension force at the bottom, we can use this equation, F equals the spring constant times the stretch, and solve for the spring constant, and we're going to come up with 675.259 newtons per meter, and we're going to use that in number 5 to find the stretch at a 30-degree angle. So once again, we use the tension force that we found in this problem, and we're going to divide that by the spring constant and come up with 1.25 meter stretch. Thank you.
So as you can see, as the ball gets closer to the bottom of the trajectory, you can see the tension force, which is the blue arrow, increasing, and as it gets to the top it decreases, and you can also see the ball speeds up as it gets closer to the bottom. Thank you for watching.